Hi folks, so here's the first lecture for Plant, Soils, and Climate 3420, Landscape Irrigation Design. Welcome to the class. We're going to begin with some basic soils information that will be important to the irrigation design process, starting with what soils are made of, which depending on your educational background you may be very familiar with, some of you less so, so we'll start there. But soils are basically made up of 50%, well, almost 50% mineral particles, 25% air, and 25% water. In addition, 5% is comprised of organic matter, and this organic matter is in turn comprised of some soil organisms, some roots, as well as some other decomposing organic material known as humus. Now, the 25% air and water occupy soil pore spaces, and I'll talk more about those as we go on. But what about that other 45% of soil, which is composed of mineral particles? Now, those are the soil solids, and they are produced by weathering of some kind of parent material, typically some kind of rock material. They almost always have distinct crystalline structures composed primarily of oxygen, silica, and aluminum. And oftentimes they're going to have appreciable amounts of other elements, things like iron, calcium, and potassium, and these minerals are necessary for plant and microbial growth, so they become very important in the long term for plant growth. So that's what soil is comprised of. In the landscape, soils are organized into different horizons or layers, and then the groups of those horizons or layers, as you see here in this particular image, together compose a soil profile. So what you see here is obviously a stylized soil profile, and everything looks very clean and neat, but it's a good thing to describe the situation for you to get a sense of what it looks like in cross-section. So here at the top there is an organic or O horizon oftentimes, and that's got decomposing plant material and things like that. Beneath that is often what's known as an A horizon, and it goes right in order, A, B, C, so that makes it easy. So the A horizon is typically where most plant roots are located, where most mineral nutrition for those plants is located, and then beyond that there are the B horizon, the C horizon, and then finally bedrock or parent material. And the depths of these things is going to be very dependent on where you are and what's happened in the area prior to you getting there. Now, this is not typically what you're going to see in a landscape that you might be working with to design irrigation. It's much more likely that you'll see disturbed profiles of the soil, and that can be because of compaction. You know, they might have removed topsoil, brought in topsoil for any number of reasons. It could be a disturbed profile, but it is still a profile, and it's still important for you to know about it as you design an irrigation system. Now, another thing that's really important as far as irrigation goes is having some understanding of the soil texture that you're working with. And the soil texture describes the amount of individual mineral particles that are either sand size, which are the largest, silt size, which are somewhere in the middle, or clay size, which are the teeny tiny ones here at the bottom. So the relative amount of those particle sizes in a soil allows you to assign a soil texture. And there are a total of 12 textural classes of the soil, including you can have a straight sand, silt, or clay, but it's more likely you're going to have a mixture of those particle sizes, and it will give you a different texture, like a sandy loam, a clay loam. There are a number of others that I'll show you here in a minute. But how do you determine that soil texture? Well, there are a number of different ways. One way is to bring soils into a laboratory situation and to dry them, and then filter them through different size sieves into these particle classes, and that gives you the amount or percentage of each of those and allows you to determine soil texture. Now, another way to do it is simply by feel. And what you see here is someone who's taken some amount of soil, it's a fairly small amount, added some water, and created a moist soil that they can work with in their hand. And people who are very experienced can do this and be very accurate as far as what the textural class of the soil actually is. Now, another laboratory technique that's often used is the use of the instrument that you see here, which is a hydrometer. And it's measured here along the stem with units, and it's weighted here at the bottom. You might be able to pick that out there. But what happens is that hydrometer is placed into a graduated cylinder with a certain amount of soil mixed in and a standard amount of liquid added. And so how this floats in that graduated cylinder helps to determine the soil texture in this case. Now, a much simpler and easy approach that anyone can do really is to mix a certain amount of soil in a jar with water. Doesn't matter what kind of jar, doesn't matter what kind of water. Shake it up and then allow it to settle. What happens is the heavier sand particles settle to the bottom, and you can kind of make out there's a line right here that's indicating a difference in the layers or sizes of particles. So sand will settle first, then silt, and then the clay. And again, the relative percentages of each can then be used to determine soil texture. So if you have those relative percentages, then you can actually work with this, which is the soil textural triangle. And this is where those 12 textural classes are described. So sand, loamy sand, sandy loam, etc. So the way this works is, let's just do a quick example. You start with the percentage of sand. So let's say in our example that our percentage of sand is 30% right here. And there's a line, if you'll notice, going up this way. So we're going to keep that line in mind. So 30% sand. And let's say that it also has approximately 20% silt. So here's 20% silt. And if you follow the line down, you want to keep that line in mind. That's what's happening on the silt side. And on the clay side, let's just say that this soil has approximately, oh, I don't know, 60%, no, let's say, so 30% sand, 20% silt, and 50% clay, okay? And also, just as a note here, you know which direction to follow the lines because of these arrows right here. So sand's going this way, silt's going this way, clay's going this way. So with our example, 30% sand coming up, 20% sand coming down, you're already getting a sense, and 50% sand coming across, that puts us here in the clay area. So in that example, we would have a clay soil that we would be working with. So that's how the textural triangle is utilized. Now, that's important, right? You need to know something about the soil texture, and here are those classes that I just showed you. But what's also important to note is how these textural classes relate to water holding capacity of the soil. So a broader description of these textures is coarse, moderately, medium, moderately fine, and fine. And you can see here that the amount of water stored per depth of soil, in this case inches per foot, changes depending on whether the texture is coarse, moderate, or fine. So for example, a coarse textured soil can only hold anywhere from half to 1 inch of water per foot of soil, where a fine textured soil, and this includes a lot of the clays, would hold 1.75 inches of water per foot of soil. So please try to keep that in mind as we go on. Now, something else that's very important is soil structure, and that relates to the arrangement or grouping of individual soil particles. And here are some examples. So these two at the bottom, granular and crumb, are generally considered the best in terms of irrigation efficiency because water infiltrates very readily. And these are formed when organic matter really has a chance to decompose and help in the development of those structures. They make it very stable. And then that soil can resist dispersion in water. So those are generally considered the best, but you can also see there are a number of other platy soil structures, one of which is platy, but there's also prismatic and columnar and blocky, and so you can see here a lot of different options as far as soil structure, and these are important because what happens is water in the soil tends to move around these various particles, so it becomes very important in terms of irrigation application. Now, what about pore space? I mentioned that a little bit in the beginning. You know, obviously those are the openings in the soil that typically contain air and water, and they're really important for irrigation because of how they influence water storage, and they're influenced by soil texture and structure. So those pore spaces are going to be different depending on the texture of the soil. For example, a coarse sand would only have 35% pore space, or a fine clay would have as much as 60% pore space. So big differences there. These can be reduced by compaction, and they're also changed by wetting and drying, freezing and thawing, root development and decay. Anything that causes soil particles to move can be actually beneficial, as it kind of reorients the soil particles, and it can encourage more pore space. Also, something to note is that small pores tend to encourage water storage, and large pores tend to encourage drainage. So this is the rate here at which water infiltrates the bare soil. And the main point is that over time you can see this intake rate slows down significantly until it kind of levels off and reaches sort of a steady state. So what this means in terms of irrigation is that when the irrigation process starts, a lot of intake is happening. So a lot of water is being taken in, but you can't just go on forever with that, because eventually it levels out and decreases significantly. So this is where you might start to see runoff, for example, if you exceed the infiltration rate or intake rate of the soil. So again, how this relates to irrigation as we go on. Now here again is some texture information, so a few of the textural classes that we've discussed here on the left. And these are rules of thumb. So there's a basic intake rate which ranges anywhere from, on the high end, 1 inch per hour for coarse sands, 1 inch of water per hour, to, on the low end, maybe 1/10 of an inch per hour as a basic intake rate for the finer textured soils like clay loam. Now, those are basic intake rates, but what if there's a poor condition like compaction? In that case, the intake rate for a coarse sand is going to be anywhere from 0.35 to 0.65 inches per hour, so significantly reduced from a basic intake rate. And this is where having some understanding of the texture and whether or not you have a disturbed profile becomes really important. The clay loam, the finer textured soil, also significantly decreased under poor conditions, so 0.05 inches to 0.1 inch per hour, so a big difference. So let's talk a little bit about storage and movement of water. Water is going to enter, move, and be stored and released from soils mainly by gravity, but also by capillary forces called adhesion and cohesion, and I'll get more into those as we go on. But the amount of water in the soil is described in the terms that you see here. So there's saturation, there's field capacity, there's permanent wilting percentage, sometimes known as permanent wilting point, and then oven dry. So those are terms used to describe the moisture content of a soil. And at saturation, all those pores are filled with water, but really this condition rarely truly exists in soils because there are almost always some pores that contain entrapped air. Now, field capacity refers to the water content in a field soil after it's been thoroughly wetted and then drained by gravity. It's an estimate of the upper limit of available water that may be temporarily stored in the soil profile for plant use. So sort of that ideal water content in terms of plant requirements. The permanent wilting point is the percentage of soil water still present in the soil when permanent wilting of plants occurs. So that's exactly what it sounds like. And at that point, the films of water around soil particles are really thin, much thinner than they are at field capacity. But they still remain, and capillary forces still operate, but the water is held at such high tension that most plants, if they've wilted during the day, can't absorb enough water fast enough to regain turgidity overnight. Oven dry refers to soil samples that have been dried in an oven at 105 degrees Celsius for 24 hours or until all the moisture has been driven out of the soil. Notice how the water, it's a little tricky to see here, but you can look at the image in your textbook. Notice how the water is stored as connecting films around the soil solids, both at field capacity and permanent wilting point. When the distance between the solids is less than about twice the thickness of that film of water, the water forms a bridge, and the adjacent solids are connected with continuous films of water. Alright, so a little bit more about storage and movement of water in soils. What happens is soil water is released between field capacity and the permanent wilting point, and this is commonly referred to as available water, so plant available water. And this is a major interest to you, or it should be, as an irrigation designer, because it has a major influence on the maximum amount of time allowed in between irrigations and the maximum amount of irrigation water that should be applied at any one time. So here you can see the general relationship between soil moisture characteristics, like field capacity, wilting point, and soil texture. So just as an example, you know, the coarse textured sand here has much less unavailable water, but much less available water, simply because it's not retaining as much water when compared to a clay, which, although it has a lot more water available, a big chunk of that is not available because of the small pore sizes, but more is available simply because it can store more water than the coarse textured soil. So I mentioned capillary forces. Water also moves and is stored in the soil in response to capillary forces, and these forces include adhesion and cohesion. Adhesion is the physical attraction of unlike substances to one another, and what it does is it holds water molecules tightly to the soil solids at the soil-water interface. Cohesion, on the other hand, is the attraction of like substances to one another, and that's what forms a film of water around soil particles, so the water is cohesive with itself. Capillary water moves or is held in the soil in response to these forces. And suction, or some kind of pressure differential, is required to move water from the film of water around soil particles, and it decreases as the water film becomes thicker and the soil moisture content increases and may approach field capacity. So, having said all that, all water is not equally available to plants, and as the soil dries from field capacity to the permanent wilting point, more energy is going to be required to move the water from the soil into the plant roots. And different plants are going to react differently to variations in the amount of available water. So the term readily available water is sometimes used to refer to that portion of the soil water that is readily available to a given plant or planting. A closely related term, and one that we'll use fairly often during this course, is maximum allowable deficiency. And the two terms are related in this way. Maximum allowable depletion is strictly related to the plant material and doesn't take into account irrigation system limitations, soil limitations, management considerations, and so forth. So, sorry, that's maximum allowable deficiency. But a term that does take those things into account is management allowable depletion. So management allowable depletion does take into account irrigation system limitations, soil situations, management considerations. And by the way, let's just relate those. So that readily available water is equal to the amount of available water based on soil texture and the maximum allowable deficiency, which is a percentage. So, and we'll go through a couple of examples with these. Now, another term you should be familiar with is plant available water, which is equal to the amount of available water times the root zone depth. And this is a function of root zone depth and soil characteristics, and it describes the total amount of water available to a plant. The term root available water is sometimes used to describe plant available water, but let's have a look at an example. So, what is the plant available water going to be for a turf area that has a 2.5 foot deep root zone? The soil is a clay loam, and we're given the information that the clay loam has 2.2 inches of water storage per foot, available water. And so the calculation would be available water of 2.2 inches per foot times the root zone depth, which is 2.5 feet, gives us a plant available water amount of 5.5 inches. Okay, so that's how plant available water can be determined. Now another term to be familiar with is allowable depletion. And allowable depletion is the amount of usable amount of available water held in the root zone. And it's sometimes referred to as allowable soil depletion or allowable soil water depletion. So an example for that one would be, let's use our same turf example with a 2.5 foot root zone growing on a clay loam soil. But if we are also given the information that the maximum allowable depletion is 50%, how much water can be utilized by plants prior to the next scheduled irrigation? So recall the equation. Allowable depletion is equal to plant available water times maximum allowable depletion percentage. So our plant available water came from our previous calculation. It was 5.5 inches. We've been given a maximum allowable depletion, which is 50%. We end up with an allowable depletion of 2.75 inches. So once that 2.75 inches of water is utilized, some water needs to be added some way. And for us, we're talking about irrigation. So an irrigation would need to occur. Now let's look at another example. What would the plant available water and allowable depletion for a cool season turf grass growing in a sandy loam soil be? Assume a maximum allowable depletion of 50% and also assume that the rooting depth of the grass is 6 inches. So I showed you a table earlier. Recall from this table that a sandy loam, which is right here, is considered a moderately coarse textured soil, and the available water ranges from 1 to 1.5 inches per foot. So for this example, let's use a middle value of 1.25 inches per foot. Okay, but that's where that's coming from. So 1.25 inches per foot. And our equations were plant available water is equal to available water times the root zone depth, and allowable depletion is equal to plant available water times maximum allowable depletion over 100. So the math works out this way. Plant available water. So available water, 1.25 inches per foot based on that soil texture, times 6 inches rooting depth, which was given to us in the example, times 1 foot per 12 inches. And that's just to help us manage all of the units that you see here. And what we end up with is 0.63 inches. Now, allowable depletion, using that plant available water we've just calculated, is plant available water times maximum allowable depletion over 100, and we end up with 0.63 inches, which we've just calculated, times maximum allowable depletion, which was given to us as 50% over 100, and end up with an allowable depletion of 0.31 inches. Okay, so those are examples of how to calculate plant available water and allowable depletion. So recall that one of the objectives for this lecture is to become familiar with the terms used to describe soil physical characteristics. And so I've introduced several of those: texture, pore space, structure. We'll keep referring back to these and how they relate to irrigation system design decisions over the course. So you should have also an understanding of soil water storage and the importance of water movement in soils as it relates to available plant water. Additionally, summary information for this lecture includes that water applied to soil moves due to gravity and capillary forces. The rate of water movement in a soil profile varies greatly with differences in soil structure and texture. Irrigation water tends to advance as a front from wet to dry soil because of capillary forces in the soil, so adhesion and cohesion. And then immediately at and behind that front of irrigation water, the soil is at field capacity or above. So I like to leave you at the end of lectures with a little bit of food for thought, and we will move on.